Student friends, once again we are continuing with topic number 5, namely oscillators. In the last week, in the last period, we studied the how oscillations are set up in tank circuit and also the meaning of tank circuit. Prior to that, we studied the definition of an oscillator, types of an oscillator, concept of positive feedback, and the Barkhausen criteria. That makes all of you to understand the basics associated with an oscillator. Today onwards, we are going to study the different types of oscillators. Actually, we have to study totally 5 oscillators. One is Hartley oscillator, second one is Colpitt's oscillator, third one is a crystal oscillator, fourth one is Weinberg oscillator, and last one is facet oscillator. Out of those 5 oscillators, we will begin with Hartley oscillator. This oscillator is being described by a scientist Hartley. That's why it is known as Hartley oscillator. Hartley oscillator is a radio frequency oscillator that generates the frequency in a radio frequency range, that is about 20 kilohertz frequency to be generated by using the Hartley oscillator. Hartley oscillator generates the sine waves at its output, so that's why it is called as sinusoidal oscillator. As it contains inductance and capacitor in the tank circuit, which is represented here, which I already studied. So that's why this oscillator again belongs to the RF oscillator. Such a Hartley oscillator consists of or it makes use of a transistor in NPN type by which emitter is common for input as well as output. In short, we can say the NPN transistor is used in common emitter configuration. The biasing network to be chosen here is with the combination of R1 and R2. That is, R1 and R2 forms voltage divider biasing network that biases the B.Sc-II, or it biases the operating point of B.Sc-II in the active region so that it is going to act as a faithful amplifier. The resistance RC, or sometimes this RC is being replaced by radio frequency choke coil, that is RFC. Its role is, it is going to act as a load on the amplifier, and also it protects the high radio frequency current to pass through the transistor, and also it avoids the short circuiting of the B.Sc-II. So that's why In most of the cases, instead of RC, a radio frequency choke is also used as a load resistance on that particular amplifier. The circuit also consists of the resistance RE, that is the emitter resistance connected between emitter and that of ground. It is going to act as a emitter bypass emitter resistor. It is used to provide self-biasing to the B.Sc-II. In parallel to that RE, it makes use of emitter bypass capacitor CE. It bypasses AC current to the ground. Along with that, this circuit contains the capacitor C1, which is used to couple the feedback signal voltage from the tank circuit to the input of B.Sc-II. Friends, this is the feedback path from tank circuit to that of base. Capacitor C2 or CU is output capacitor that is used to couple tank circuit to the amplifier circuitry. Friends, it also consists of a tank circuit which is formulated by the parallel combination of capacitor C to the series combination of L1 and L2. L1 and L2 in series form the total inductance as a L. Dear students, the tapping is done between L1 and L2 and that is grounded. It is generally referred as the center tapping of the two coils that divides number of turns of inductance into two R. Number of turns of L1 is 2/3, whereas the number of turns of L2 is 1/3. If you make use of single coil, then you have to arrange the number of turns in such a way that L1 possesses the 2/3 turns and L2 possesses 1/3 turns. Meaning thereby, if you wound say 100 turns totally L1 plus L2, out of 100, 66 turns are associated with the L1 and 33 turns are associated with the L2. Exactly their center a tapping is done and it is grounded. In parallel to that, a capacitor C is connected that forms the tank circuit, and we know how tank circuit works and how oscillations are generated in the tank circuit, which I already studied in the last period. Friends, this is what the construction of the Hartley oscillator. Now, to sustain an oscillations, we are aware that it has to satisfy the two conditions. That is, it has to satisfy the Barkhausian criteria, and that is the feedback must be positive and the internal loop gain KAV should be greater than or equal to 1. Students, please do remember that as a transistor used as an amplifier is in the common emitter form, we are well aware that the phase shift between output of the amplifier and that of the input is 180 degree. So output waveform generated at the collector and input associated with the base of the B.Sc-II are out of phase by 180 degree. Thus, 180 degree phase shift is generated by means of an amplifier circuitry. Whereas, remaining 180 degree phase shift is generated by the tank circuit. Thus, 180 phase shift by tank circuit and 180 phase shift by amplifier circuitry, totally this phase shift is added or subtracted. If it is added, net phase shift becomes equal to 360 degree. If it is subtracted, net phase shift becomes equal to 0 degree. And we studied in the Markusian criteria that if the phase shift of total oscillatory circuit is either 360 degree or 0 degree, then there will be a positive feedback path. And we know that a positive feedback path is there, which is applied from the output of tank circuit and it is given back to the input of the amplifier. This is what we can call it as the feedback path. This one of the condition of Markusian criteria is automatically satisfied here. If you adjust the value of beta or value of HFE, that is forward current gain, is equal to L1 plus M upon L2 plus M, where M is the mutual inductance, then internal loop gain KAV also becomes equal to greater than or equal to 1. Hence, the second condition is also going to be satisfied. And hence, the circuit is now ready to sustain an oscillations. Now, how oscillations are going to be get generated? That's what we can call it as it is a working of Hartley oscillator. Friends, as a being VCC is provided to the amplifier circuitry formed by the B.Sc-II, its operating point, it allows base current to pass through the B.Sc-II by using R1 and R2. Its operating point is going to be managed in the active region so that it will start acting it as an amplifier. When it starts acting it as an amplifier, the collector current will start flowing through the collector. The coupling capacitor blocks the DC and allows only path for AC. When collector current passes through the tank circuit, the capacitor C will start charging with the polarity upper terminal positive and lower terminal negative. When capacitor fully charges by the working of tank circuit, electrostatic charges will be converted into electromagnetic lines by discharging the capacitor through the combination of L1 and L2, so that lines of magnetic field will be starts building up across L1 and L2 in a particular direction. Under that particular condition, the capacitor fully discharges and full magnetic flux will be developed across L1 and L2 till the steady state is being reached. Once the steady state is being reached, means if dic by dt becomes equal to 0, then we can say steady state of magnetization is reached across combination of L1 and L2. As the being capacitor is completely discharged, now magnetic flux will starts collapsing. And when magnetic flux becomes collapsing, capacitor C will start charging with the polarity opposite to that of previous one. That means lower terminal positive and upper terminal negative. When magnetic flux fully collapses, capacitor fully charges and lower plate becomes positive polarized, whereas upper terminal becomes negative polarized. This signal is given back to the input. As the being transistor is NPN, transistor is again forward biased due to positive signal provided to the base, and again transistor will be turned on, it will start conducting the current. This current will again passes through the tank circuit. Meanwhile, the capacitor again discharges and this reverse current also flows to the inductance combination of L1 and L2 to start building up the magnetic flux but in opposite direction. This will continue till capacitor fully discharges and steady state of magnetization is reached. Again magnetic flux will collapses and capacitor will start charging with previous polarity, that is upper terminal positive and lower terminal negative. When lower terminal becomes negative, base biasing will, emitter and base is reverse bias and transistor is going to be turned off. Thus, the electrical oscillations are set up. Electrical oscillations are sustained by the charging and discharging of capacitor and also building and collapsing of the magnetic field across the inductance L, which are feedback to the input. This provided feedback signal will be amplified by means of an amplifier formed by the B.Sc-II and its respective passive components. So amplified oscillations are made available at the collector of B.Sc-II, which one can observe by using the CRO, that is cathode ray oscilloscope, and these will be in the form of sinusoidal nature, and that's why we can call it as it is a sine wave generator or sinusoidal oscillator. The value of C and L should be chosen as small as it is possible so as to get the frequency more than 20 kilohertz, and that's why we can say it is a radio frequency oscillator that can be used as a local oscillator in the demodulation process. It is also used to generate the carrier waves in the modulation process. But when impedance of this particular tank circuit becomes equal to 0, then the resonance will take place in the tank circuit. And when the resonance will take place, naturally maximum resonating frequency will be generated, and that is what we can call it as the maximum frequency of this particular Hartley oscillator. Thus, at resonance means to occur resonance in the tank circuit, the total impedance of LC tank circuit should becomes equal to 0. Means when impedance of tank circuit, that is impedance of inductance L1, J omega L1, impedance of inductance L2, J omega L2, and impedance of capacitor, that is 1 upon J omega C. When they becomes exactly equal, then net impedance becomes equal to 0. And when net impedance becomes equal to 0, then we can say maximum resonating frequency will be generated, and that is what we can call it as it is a frequency of an oscillator. To calculate that particular frequency, we are equating now impedance of tank circuit, that is Z equal to J omega L1 impedance of plus J omega M, where M is the mutual inductance between L1 and L2. L1 is the inductance L1. Then next will be J omega L2 plus J omega M plus 1 upon J omega C. This is the impedance of tank circuit, where M is the mutual inductance. By separating J omega term, or J omega L1 plus J omega L2 plus 2 times J omega M plus 2 times J omega M plus 1 upon J omega C. We have combined all these terms together. Now take the j omega common from this. When you take j omega common, we can get L1 plus L2 plus 2 times m minus 1 upon omega square c. But at resonance, z is 0. So that's why equating this term to 0 so as to get j omega into L1 plus L2 plus twice m minus 1 upon omega square c equal to 0. J omega can't be 0. Therefore, L1 plus L2 plus twice m minus 1 upon omega square c equal to 0. By transferring minus 1 upon omega square c to the right side so as to get L1 plus L2 plus twice m equal to 1 upon omega square c. Taking the reciprocal, we can say omega square c equal to 1 upon L1 plus L2 plus twice m. Therefore, omega square equal to 1 upon c into bracket L1 plus L2 plus twice m. Therefore, omega is equal to, taking square root on both sides, omega is equal to 1 upon square root of c into L1 plus L2 plus twice m. By putting omega is equal to 2 pi f, we can rewrite this equation as 2 pi f equal to 1 upon square root of c into bracket L1 plus L2 plus twice m. That is, f is equal to, taking 2 pi on the right side, f is equal to 1 upon 2 pi square root of c into L1 plus L2 plus twice m. Now by substituting, L1 plus L2 plus twice m is equal to L. So as to get f is equal to 1 upon twice pi root of LC. Obviously, we have put L is equal to L1 plus L2 plus twice m. Dear students, this is the formula for frequency of Hartley oscillator. From this equation, we can directly say that frequency of Hartley oscillator is going to depend upon value of L and C. F is inversely proportional to square root of LC. 2 is constant, pi is constant. You can design your Hartley oscillator as per your requirement of frequency. Choose the proper value of inductance and capacitor so that you are going to get the required frequency of sinusoidal oscillations in the Hartley oscillator circuit. Dear students, there will be numerical examples which are going to be asked on this particular formula. Now, as already one of the condition of Barkhausen criteria is satisfied so as to give the phase shift between amplifier is 180 degree, phase shift produced by tank circuit is 180 degree, so that net phase shift between input and output of an oscillator is either 0 degree or 360 degree so as to satisfy the condition of positive feedback. Now, to get the oscillations and to satisfy the second condition, that is KAV, that is the internal loop gain, is becomes equal to or greater than 1. This is done provided the current gain of transistor, that is HFE, is equal to L1 plus M upon L2 plus M. If this condition is satisfied, then KAV becomes equal to greater than 1. Positive feedback is already existing, means Barkhausen criteria is satisfied, and as we have seen the working accordingly, the oscillations are set up in the tank circuit which are feedback to the input of the amplifier. It is amplified, its amplitude level is amplified, and it is made available at the output of Hartley oscillator. Friends, that's all about the construction, working, condition, how it is going to satisfy the Barkhausen criteria, formula for frequency of Hartley oscillator, and how it can be used to generate the radio frequency signal at resonating condition. That's all about the Hartley oscillator. Next oscillator we are going to study in the next time.